All right, so today we're just going to go with more examples or algorithms if we want to. But yeah, everybody said that you were looking at sorting algorithms already in another course, so I don't know. How many people want to see insertion sort?
R235 is not
Oh, okay, all right, then let's look at insertion sort then, as another example, okay? All right, so insert from, actually, no, I'll show it to you on an array here first, right? So the idea is that you might be able to exploit the fact that the array is almost sorted already in order to do less work, right? When we talk about data structures and algorithms, why do we like structures? Because structure can be exploited. And we'll see that with trees when we look at those. So how could we exploit the fact that it might already be sorted, right? So for example, what if the first 4 elements were sorted, right? So in other words, looking at just these first 4 elements right here, what if they were already sorted for us? We got that for free, right? There we go. Now, ignoring the rest of it, and we're just looking at 102 here, 102, right? We just need to find out where that needs to go. But now guess what? 4, 4, 9, 42. With respect to just these 5 elements, again, we're ignoring the rest of this for now. We'll save that for later. Do I need to change its position at all? No. I got away with doing less work. How did I know that I didn't need to change positions of it? I simply just compared it to what's right next to it. Knowing that the rest of this is already sorted means that I only had to do one comparison to see that it was where it needed to be. Now, there is a trade-off here, right? For example, what if I were to look at the next value here? Let's go ahead and suppose that we've got 4, 4, 9, 42, and 102 now. That's my sorted section of the subarray. And now I'm looking at 34. So now is 34 where it needs to be? No. Where does it need to be? Right here. Right? But do I need to look at the entire list here, or the entire array, in order to determine that? No. I'll simply just compare it to the one right next to it. They're out of order, so what should I do? Swap it. Compare it to the next one. They're out of order, so swap it. Compare it to the next one and see that they're not out of order. 9 and 34, the thing that I'm shifting down here now, that I'm inserting in a location, they're in order. So I got away with only 3 comparisons and say 2 swaps, right? To end up with something that looks like this. 34, 42, and 102. So it's now 34, 42, and 102. And I've extended the area of this array that is sorted. Right? I should have checked. Hopefully the audio is going. It looks like it. I never bothered to check it though. Sorry for anybody that's streaming this. Yeah, we're good. All right, you can take that off now. I can take these off. There we go. All right, so this is the basis of selection sort. Sometimes you might get away with only one comparison, right? Sometimes you might end up having to compare it with everything previous to it because it's the minimum element. For example, if you fast forwarded here and all of this stuff here was rearranged so that it was sorted, 0 down at the bottom here, what are you going to end up doing? Comparing it to everything just to shift it all the way down over here. Okay? So sometimes you get away with less work. Sometimes you have to do all the work. Right? But on average, is this a little bit better? First of all, let's go ahead and look at the algorithm itself here. Insertion sort. There we go. Here is the actual pseudocode. I'm going to walk you through it. I didn't want to write this from scratch. All right, so I've got this outer for loop here. Right? What that's going to do is it's going to run from the second element all the way up to the first element. Why are we skipping the first element? If you just look at one element and you ignore everything else, by definition it is sorted. So we end up looking at the second element to see if do we need to shift it down. Okay? That's why we're starting at 2, and we do go up to and including n. Why? Because again, fast forward. If all of this is sorted, right, do we have to worry about that last guy? Yes. Right, we have to make sure that he's inserted where he needs to be, or maybe he's all the way down at the end here. Okay? So our outer for loop here is going to concentrate on the entire array, but skipping the first element. Now, what are we doing inside of that algorithm? Well, this is saving off a temporary variable, right? What I'm doing is save off a sub I to a temp variable. Why? Because the idea here is that if I'm looking at a sub I, I'm going to put that off into a temporary variable, x. Why? Because I'm going to look at a sub I minus 1 and a sub I minus 2. Right? And ultimately, I need to determine, should I shift this thing up because I need to insert x there? I don't want to have to swap. My original presentation here was swap. But all I'm going to end up doing is saving this one off and then shifting them instead so that I don't have extra work. Right? I have then j here. J is going to run from I minus 1, or the one previous, excuse me, and then it's going to go down, 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 down. What happens if we go all the way to the beginning here? Should I keep going past 0? No. That's why I've got this check right here. And again, this is 1 indexed. So while j is strictly greater than 1, and these things are out of order, I'm comparing x now to this one, and it's out of order, so I need to shift this up. I'm comparing x to this one, and it's out of order, so I need to shift it up. That's the idea. I shift it up, and then I decrement j, because I need to look at each one at, previous to it. By decrementing j, I simply mean j minus minus. Right? Now at the end, I need to take this x and put it back where it needs to be. I need to insert x. Right? So this ends up inserting a sub I, which is equal to x, where it needs to be. Right? Done. Okay? There are my annotations. Let's actually analyze this algorithm. Right? And again, it's called insertion sort y because it inserts those things where it needs to be. Right? Okay. Well, remember, the reason that I considered this approach is because sometimes I can get away with things and not have to do too much work. Other times, I need to end up doing a lot of work. So let's split this up into 2 cases. What's the best case scenario? Here, let me rewrite this. For each iteration, I, the best case scenario. For example, 101 here. If this was all sorted already, did I need to shift it down? No, but I did need to make one comparison. So, what are the number of comparisons? Number of comparisons, comps, and shifts. The number of comparisons would be 1 to see that you don't need to shift it, and therefore 0 shifts. What's the worst case? The worst case is, for example, when you get down to the very end here, and all of this has been sorted, right? But then you've got this one, and you need to shift it all the way down to the beginning, right? So if I'm looking at this from the perspective of the ith iteration, then that means I've got elements a sub 1, a sub 2, a sub I minus 1, and I've got a sub I here. And then the rest of it, a sub I plus 1 all the way through a sub n. Okay? This is the thing that I need to determine where I insert it. Therefore, how many things are still over here? I minus 1. So at most, how many comparisons do I need to make for this thing to see that I need to shift it all the way to the beginning? I minus 1. So I minus 1 comparisons at most, in the worst case. How many shifts? I shift all I minus 1 of them up, right? And then I of course insert this one where it needs to be. Right? Okay. I left a big gap here. Why? what's the average case scenario? Now, once again, to actually do this in a rigorous mathematical sense, you need to do this for all possible permutations, assume a uniform distribution on all possible permutations, blah, blah, blah. Guess what happens? You come up with I minus 1 plus 1 all over 2. Why? This is the worst case scenario plus the best case scenario divided by 2. Simplify that for me, math majors. I divided by 2. Right. And therefore, I divided by 2 shifts. Okay. Should we even bother with the best case scenario? Best case scenario, you end up doing what? I is going to run from 2 up to n. So what's the number of comparisons that you make if you make 1 for each iteration? You know what? Let me move this over and go overall. Overall performance here. You end up doing n minus 1 comparisons. Right? This is each iteration. Overall, you do n minus 1. Why? Because you skipped that first one. You didn't make a comparison for it. But you look at everything else and you never end up making any shifts. Why? Because everything's already in place. In other words, it was already sorted, and you're just verifying that it was sorted. Right. Can you assume that linear behavior, though? No. That's the best case scenario. Right. What about the average case scenario? You're doing I divided by 2, I divided by 2, plus I divided by 2. How many times? I running from 2 to n. So let's do that over here. Summation of I running from 2 up to n of I divided by 2. What can you do with that divided by 2 already? Take it out front. Right? And now you're going 2, or I is equal to 2 up to n of I. In other words, 2 plus 3 plus 4 plus 5 plus 6 dot 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 plus n. Does that look familiar? That's Mr. Gauss again. 1/2 n times n plus 1 all over 2. But careful, you skipped 1. So how do we correct for that? Simply just subtract 1. Okay. Distribute, distribute, distribute. Magic algebra. 1/4 n squared plus 1/4 n, right, minus 1. Is that right? All right, so what about these lower order terms over here? You can ignore them, right? Because this highest order term here is what's going to control it. But think back to selection sort. Selection sort, we had something sitting out front 1/2 n for selection sort. Right. And what do we have here? 1/4. So which between, now you are asking an engineering question. Between these two sorting algorithms, which one should be better in practice? Selection sort with 1/2 n, or 1/2 as many comparisons on average? Which one? Insertion sort, right? This is, smaller is better. Why? Because you're doing less work. Right? So this is going to be 1/4 n squared, about. Okay? What about the worst case scenario here? I minus 1. Let's do that analysis. Right? I minus 1. Summation of sums is equal to the sum of summations. So we have a summation of I running from 2 to n of I minus summation of I is equal to 2 to the n of 1. Right? Ooh, that's already looking really, really familiar. Right? The first one is Gauss's formula again. N times n plus 1 all over 2 minus 1 because we started at 2 minus, and then that's 1 plus 1 plus 1 plus 1 how many times? N minus 1 times. Right. Algebra, algebra, algebra. You'll come out with that this is about 1/2 n squared. And again, you could probably ignore this when we get to asymptotics, we will definitely ignore that. Right? But 1/2 n squared. Now I've got both of them implemented here. Unfortunately, it doesn't work out. I have no idea why it's not working out for me. But you can see the performance here, that this is a quadratic sorting algorithm. I've got insertion sort right here. If it's going to take, I think, 0.05 seconds for 10,000. If I go up to 100,000, it's going to be about 100 times slower. Why? Because it's quadratic. 10n, if I go from n to 10n, it's still squared. What happens to that 10? It becomes 100. And so this is going to be almost 5 minutes here. Or 5 minutes, 5 seconds. Right? About that, 1/2 of it. If I went up to, say, 200,000 here. Now I'm not going up by a factor of 10, I'm going up by a factor of 2. So what's 2 squared? 4. So 3 seconds becomes probably 4 times as big, 12 seconds. While we're waiting, you can see the implementation up here. There's selection sort, it's just a direct translation. There's insertion sort, it's just a direct translation. If you're interested in any of the code for any of this stuff, you can go ahead and check out the CS1 textbook, my CS1 textbook. Right? What did I say? 12? Oh man, almost dead on there. Right? Now, when you're looking at small inputs, 100 or 200, there's not going to be an appreciable difference between these two algorithms or even between run times. 100, 200, right? It's not even measurable. That's not what matters, right? Everybody is good on small things, right? Everybody can do the shapes into the shapes, right? The hexagon into the hexagon. Everybody can do simple stuff. These algorithms, I'm anthropomorphizing these algorithms, but they're fast on, everything is fast on small inputs. It's what happens when you get up to large inputs that it matters. What was this? 12 seconds? Right. So can we do better than insertion sort or selection sort? Yes, by not doing your own sorting algorithms at all. Arrays dot sort, there we go, and list. All right, remember that this took 12 seconds on 200,000? No, orders of magnitude faster. I'm comfortable going up to, say, 10 million here. Still nothing, right? I'm okay with going up to, that it was 10 million, right? Oh no, that was 1 million. Now I'm at 10 million, right? I can imagine that this is going to be about 10 times slower, so it's only going to be 0.5 seconds or there. Yeah, even less. Right? 100 million. Let's keep pushing our luck here. This is going to be about 3 seconds. So now it becomes, noticeable, but it ain't going to be 20 years like the other estimates would be. Right? So what is going on inside that sorting algorithm right there? We'll talk about that next week. What I wanted to do is take care of that 5th step. So I want to focus on math for the rest of the day. Hopefully we're all okay with that. Math good? All right, cool. All right, so let's talk about big O analysis. For that, let me go ahead and give you the definition first. All right. We'll just start out with it. Asymptotics. So once again, I label this as step 5. We've kind of skipped it up till now, but now we need to actually pay attention to it. Our motivation, as we just saw from that demonstration, is that we want to characterize an algorithm's performance or efficiency with respect to the input size n. Right? We're not interested in small values of n. Why? Because everybody's good for small values of n. That should be a lowercase n, sorry, there we go. We want to know how our algorithm performs as n, right arrow, infinity, tends towards infinity. Look familiar? Calculus. What do you do in calculus with respect to n tending towards infinity? You're trying to find a limit of some sort, right? Does it converge or does it blow up, right? What happens as we consider input sizes larger and larger and larger, right? We want a tool to do this that will focus on the rate of growth. Again, seem familiar with calculus, right? Rate of growth, first derivative. You're going to end up ignoring the lower order terms because when you take the first derivative, what happens to those lower order terms? They disappear, right? You're going to ignore constants, right? Because constants, who cares? You can always upgrade your hardware, and now it's twice as fast. And the tool that we use for this is big O analysis, right? Big O simply stands for Omicron. O is Omicron, right? Or here, let me show you what it looks like in LaTeX. There you go. And there is no, like Omicron, there is no LaTeX Omicron. I wonder, is there a lowercase Omicron? Let's find out. Omicron. Nope, there's no lowercase Omicron either. Why? Because it's just lowercase o. I'm not a language expert. Did our alphabet system just steal Omicron directly from Greek? Probably. We didn't do the rest of them though, right? So alpha, alpha looks like that. Oh no, it is. Did we steal it? Alpha. No, we stole uppercase alpha apparently because there is no LaTeX for it. What about beta? What? It's not doing caps? It's not doing any caps now. Beta? Oh, come on. Okay, there, it's lowercase beta. Gamma? There, little lowercase beta. Oh, so what does a Greek letter beta look like? Just a B? Yeah. Okay, so we did steal them. We stole a lot of them apparently, right? There is no Omicron in LaTeX. And here's a beautiful LaTeX. Oh, come on. Oh. There we go. There's LaTeX. There's proper LaTeX. All right. So, what is our definition? Our definition is going to be a very, very calcy-looking definition. Right? We're going to look at it from a couple of perspectives, though. We're going to look at it from an algebraic perspective. In fact, two different algebraic perspectives. Then we'll look at the calculus perspective. We have two functions, f of n and g of n. They're two functions. For our purposes, they represent the complexity of two different algorithms, a and b. We say that f of n is big O of g of n if there is a positive constant c and an integer n naught such that f of n is less than or equal to c of g of n for all n greater than or equal to n naught. Lots of wordiness there, right? All it's saying, though, is that at some point, this function is greater than that function, and they will never, ever meet again. Right? That this one is always going to dominate this one. It's always going to be larger. Right? That's saying that g is larger. This less than or equal to, that's what's quantifying it. Okay. Now, some notation here before we get into it. Right? It is most proper to say that we say that f of n is in O of g of n. Right? And especially if you've had 230 or 235H, you should definitely be using that notation. What is that little notation right there doing? It's saying that this function is in this set of functions, in this class of functions. That's the proper way of saying it. It is okay to say that f of n is, it's an abusive notation, but whatever. If everybody abuses it, then it's not abuse. Right? G of n. Right? There we go. If everybody does it, it's okay, right? Jumping off the bridge or whatever. No, don't do that. All right? It's okay to say that f of n is equal to g of n. Right? It is an abusive notation, but everybody does it. What is the intuition here? Intuition. The intuition is that f of n is bounded above after a certain point by g of n. In other words, f of n, g of n is asymptotically larger than f of n. Or to flip that around, if we did it from the f of n's perspective, f of n is asymptotically less than g of n. And that's where this less than or equal to thing comes in. F of n is less than or equal to g of n, right? It makes sense when you just look at it from the algebraic perspective. But we're talking about asymptotically here because it's not always the case, okay? Did I close my Wolfram alpha? No, okay. So let's go over here and let's write down some functions and then we're gonna look at them. So suppose that f of n is, say, 30n, right? Big coefficient there, but it's a linear function. G of n is, say, n squared plus n, right? Something very, very similar to what we just derived, okay? I want to plot those two things. And so I'm going to get Wolfram alpha to do it for me. Plot f of n is equal to 30n, g of n is equal to n squared plus n. And let's only focus on it for small values, 0 up to 10, okay? Ignore that first plot, it's a parametric plot. I want the actual plot here, right? The blue line is 30n. The red line here is n squared plus n. Now remember, what are we quantifying again? We're quantifying the performance of an algorithm. So in other words, lower is better. Why? Because the y-axis represents time or memory or resource. So if I only look at input sizes 0 up to 10, what impression do you have here about these two functions? Which one is less? N squared. Does that follow your intuition about the growth rate of these functions? No, right? This is definitely the larger function, right? Okay. Let's expand this out to, say, I don't know, 40. 0 to 40. Right? By the way, why am I not looking at the negative values? Is there such thing as a negatively sized input, an array of negative 10 elements? No. All right. Oh, okay. If we expand this out, I see that they meet at some point. In other words, at some point, they're predicted to have exactly the same behavior. Right? After that, what happens? Right? If I expand this out even more to, say, 400, right? Are those functions ever going to meet again? Probably not. Right? At least that my intuition tells me not. Okay? That's what big O analysis is saying. It's saying ignore those lower values because the functions could, they could mix and match and cross over each other at some point, right? This function will always be greater than this function, and that's what big O analysis is quantifying. The n naught here is that point. For all n after that point, all n greater than or equal to n naught, f of n is less than or equal to g of n by some constant. Okay, we'll talk about that constant here in a little bit. Okay. How do we go about proving something like this? Right? Well, let's assume no calculus, for example, for now. Right? I want to prove this. Here's my proof technique A. Proof technique A, I'll call it. Right? Find that crossover point. Right. I already did it graphically. Let's zoom back in. Come on, there we go. It's somewhere around 30 or something like that, right? Now, 235 is a graph a proof? No. Is a picture a proof? No. Not in math, right? So, how do we go about proving this? I need to find that crossover point. In other words, one of these two functions equal. When is f of n equal to g of n? Well, one is 30n equal to n squared plus n. All right, let's go ahead and take it over to another slide here. N squared plus n is equal to 30n. Right. Well, what could I do? I could take one to the other side, right? So n squared minus 29, oops, sorry, 29n, right? Y, n minus 30, or 1 minus 30 is going to be negative 29, and that's now equal to 0, okay? So what value of n satisfies this? What's one value? Yeah, how many values of n satisfy this? How many? 2. Why? It's a square, right? This looks a lot like a what? Plus 0 is equal to 0. This is an squared plus bn plus c is equal to 0. How do you solve for n now that you see it that it's a quadratic polynomial? What's one tool that you can bring to bear? No? This should be like driven into your brains, right? By now. Negative b plus minus square root of b squared minus 4ac, right? You could go ahead and plug and chug. Or you could realize that I chose these values very specifically so that we didn't have to do a lot of work. What's one root of this thing? 0. Because I can factor out a 0. Right? Once I've done that and I've gotten rid of that, what is it? Negative 29 is equal to 0. And so what's your n? 29. But if it doesn't work out like that, and you've got a plus minus constant or something like that, you can always fall back on the quadratic formula. That works for polynomials of degree 2. What about polynomials of degree 3? Do you know, is there a cubic formula? Well, there is, but it's like a step-by-step process, right? If this, then that. If not, then this, right? What about degree 4? Degree 5, 6, 7, 8? Do you want to do that stuff? No, I don't either. So you could put it into Wolfram Alpha, or we're not going to give you anything that complicated. Right? Instead, we're going to give you better techniques. Okay. But otherwise, this tells me that those two values, like if I were to graph this manually over here, right, looks something like this, they match at 0. That's our first root. And then, I drew it wrong. Let me write it like this. Right? And then at 29. There we go. Right. So from 0 to 29, it looks like the quadratic algorithm is better. But after that point, no. Like 1 explodes in performance. Explodes as in like performance degradation. And 1 just keeps on as a linear function here. Right? So my proof here is that f of n is, here, I don't want to use that bad notation. I'll encourage you to use the correct notation here. Big O of g of n. And my proof is, for all n greater than or equal to 29, right, which that's my n naught, right, f of n is less than or equal to cg of n for c being 1. Right? The c goes away because I already found this, this crossover point here, right? That inequality holds. Why? Because I solved the roots, right? And it says that 30n is less than or equal to n squared plus n for all n greater than or equal to 29. Right? That's f of n, that's g of n. C, being 1, disappears. Okay? That's proof technique A. Again, if I gave you a degree 20 polynomial with a bunch of exponential values thrown in for good measure, along with a bunch of logarithms thrown in just to confuse the hell out of you, right? Are you going to want to use this proof technique? Probably not. Proof technique like this is simple. Or if you use a tool and say, hey, Wolfram Alpha, give me all the roots of, I don't know, n to the 40 plus n minus 30 plus n to the 30 minus 3.5 times n to the 10 plus. What are all the roots of that degree 40 polynomial? There you go. Oh, I've got imaginary roots, that's why. Right? Imaginary roots would be completely irrelevant. Oh, here's a good question though. What about negative roots? Over here on the negative side of the graph. Again, do we have a negatively sized input, a concept of a negatively sized input? No. So you can easily ignore all of these except for this one right here, right? After 1, right? And then bump it up to 2 because we're only talking about integers. Okay? Again, the definition is for all integers. Why? Because there's no such thing as an array of 3.5 inputs. Okay. All right, that was proof technique A. Here's another algebraic proof technique B that I like a hell of a lot better. Right? Technique B. Right? In the first technique, what we did is we fixed C to be 1, and then we found N naught. There are two unknowns here, C and N naught. If you fix one, now you've got one unknown, one equation, you can find the other one. So what I'm going to do is I'm going to fix N to be 0, and then find C, such that f of n is less than or equal to C of g of n. Right? For all n greater than or equal to, sorry, this should be n naught, which I've already fixed to be 0. Okay? Now, I might have to change n naught as I go along here, but it's going to be way easier. I need to show this inequality, so simply start with the left-hand side here, 30n. What is it less than or equal to for all n greater than or equal to 0? Well, it's certainly less than or equal to 40n, right? It's certainly less than or equal to, say, I don't know, 2 to the n. Well, is that true? 30, 1, n is 1. Is 30 less than or equal to 2? No. 2. Is 60 less than or equal to 4? No. Right? And now we're back to proof technique A. Right? I don't want to make it too big. I want to make it look like, we want to make it look like something like this, C of n squared plus n. Why? Because this thing right here is g of n. Right? How do we make it look like that? By making it bigger. Again, it's an inequality. It doesn't have to be exact. If it's exact, then you're on proof technique A. Right? So, how do I make it look like this? By making it bigger. No? Well, twice as big. If I make it twice as big, is it still bigger? So 30n plus 30n. 30n. There we go. That's true, right? For all n greater than or equal to 0. Okay. I could factor out a 30 immediately, but would that get me anywhere? N plus n, that's just 2n. It does make it look like this. Right? What about this? What if I change the first one to 30n squared? And I get it that this goes against every instinct that you have with respect to algebra, because algebra, you're always trying to prove what? An equality, right? If you multiply the left-hand side by a, you need to multiply the right-hand side by a. Get rid of that intuition. That's not what you're trying to do. What you're trying to do is show an inequality. So making the right-hand side bigger and bigger and bigger and bigger until it looks like what you want is perfectly fine. You can add stuff, you can multiply by stuff, just don't go too far. Except that, can you do that? What about negative values? Well, we don't have any negative values, do we? Right? And besides, this is squared, right? So negative values become positive. But if I had, say, n cubed, could I necessarily say that n squared is less than or equal to n cubed for all values, for all positive values? All positive values, yes. But what about all values? Nope. This will certainly be less because negative times negative times negative is still negative. But again, we are restricting ourselves to positive inputs. Now factor out a 30. Oops. Factor out a 30. Does that look like that? Yep. For C, for n naught being 0, which we fixed, and C being 30, guess what? We just proved, using the definition, that those two functions have that relationship. Okay? So there are two proof techniques that we just showed. Okay? And we've got 10 minutes. We can show the third. Proof techniques. Right? you can fix C to be 1 and find the crossover points to prove that the inequality holds after the largest crossover point, which is your n naught. N naught, there we go. Or B, A. B, what you can do is you can fix n naught to be 0 and find your C. Find a C that satisfies the inequality, right? And again, I'm going to emphasize here AC, right? There is nothing special about 30. I could have made it 60. I could have made it 1 billion, right? And the proof technique still would have worked. Algebraically, by the way, what does it look like that I'm doing? Let me go ahead and go back. There we go. All right. There, that's the one I want, right? So let's actually go out to 35, let's say. So there are the two functions being graphed there. If I multiply g of n by some constant here, c times this thing, for c being 1, c being 1, I get the same exact graph as before, right? What am I doing by making c bigger, though? 2. All right, there it is. There's the crossover point right there at about 29. If I make it twice as big, what have I done to that crossover point? I've steepened this curve. Now the crossover point is over here. Right? What if I keep going? What if c is 3? I've steepened it even further. But have I changed the rate of growth by multiplying by a constant? No. Now the crossover point is way down here. Keep doing that until you get to some value, like say 30, where the crossover point now becomes 0 itself. Right? I can zoom in on that and say 5. Or no, I wanted 30, sorry. 30 here, and then I only want to go up to 5. Right? There, it's basically there already. Right? All I'm doing is making this steeper and steeper and steeper, pushing back that crossover point until it hits 0. Do you guys use tools like Wolfram Alpha? You do? Okay, like just to visualize stuff and stuff like that? Right? All right, good. Now here, we'll focus more on this when we get back on Monday, but I'll give you a preview of it now. Tell me about limits. As n tends towards infinity, of the ratio of two functions. Right? One of 3 things is going to happen. What if it converges to 0? What does that say about the relative growth rates of these two functions, the numerator and the denominator? If it goes to 0, what happens? G is asymptotically greater, and so we say that f of n is big O of g of n. Right? Why? Because if it converges to 0, this one's growing way faster than this one up here. Right? The denominator getting bigger, bigger, bigger makes the entire ratio go smaller, smaller, smaller until it hits 0. Right? What's another thing that could happen? It could converge to a constant which is greater than 0. What happens then? What is that kind of telling you? The growth rate of this one versus the growth rate of this one. They're kind of the same because it's converging to a constant. So f of n is big O of g of n, and g of n is big O of f of n. In fact, we have another term for this. We say that f of n is theta of g of n. That's an asymptotic equivalence. It has a different definition. It's bounded above and bounded below. We won't get into that, though. 235, getting into that? Big theta, big omega, and big omicron, big O? No? Okay. What's the third thing that could happen? It could blow up in your face. And if it doesn't converge, it diverges off to infinity. And if that's the case, then you have that g of n is big O of f of n. Now why is that? If it goes off into infinity, that means that this one is growing much faster than this one. So this one is asymptotically larger than g of n. Awesome. Why? Here's my proof technique now with those two other things. Of f of n, which was 30n, all over n squared plus n. Tell me about that. Well, yeah, why? So, I'm not going to require an epsilon delta proof, like maybe calculus requires epsilon delta proofs, or limits. I'm not going to require that kind of a proof, but show me something at least. Why does it go to 0? I've got a monotone increasing function on top, monotone increasing function on the bottom. Right? I'm not yet in obvious land that I can say, yeah, it's 0. Right? If I was 1 over n, you're in obvious land. Right? 1 over n squared, you're in obvious land. Monotone increasing function on the bottom, constant function on the top, it definitely goes down to 0. Right? But this one's not so obvious. Oh, okay. Yeah, let's say his name again. Yep. The hospital. Yeah, the hospital. Le hospital. And I think that there's a little caret there and umlaut something over there, whatever. Who cares, right? So what did I just do? You take the first derivative on the top, first derivative on the bottom. What do you get? What's the first derivative on the top? 30. Bottom? Derivative of the sum of two functions is equal to the derivative of each, the sum of the derivatives. So 2n plus 1. Now you're in obvious land. Monotone increasing function on the bottom, constant function on top. I do not require an epsilon delta proof here. You can go ahead and say what? 0. You could do another application of L'Hopital's law, and what do you get then? Well, 1 over what? 2, right? Yeah, what happens at the top? That's 0, right? Right. And so, what do you get then? Yeah, 0. So you could go one extra step if you really wanted to, but no. I'd say that you're in obvious land right here at this point. Okay? All right, so your calculus tool bag will be very helpful if you want to show things that are by this limit method here. Right? L'Hopital's law, first derivatives, algebraic. I'd look for algebraic simplifications first. Like what should you have done maybe instead? Oh, you could divide by n squared. Okay, that's interesting. I was just going to go ahead and factor out an n and cancel it out, right? This is the limit as n tends towards infinity of 30n out front, and then n of 1 or n plus 1. Right, and then what happens to those n's? They cancel out, and then you're back right here instead of having 2n on the bottom. And then you're in obvious land again here. Look for algebraic simplifications first, then bring your calc tools to bear. L'Hopital's law, first derivatives. Or you can always go with those other proof techniques too. If you're asked to do one or the other, you got to do that one or the other. So you do need some practice in all of them. And by the way, a lot of homework 8, the last homework, you can get started on that in parallel with all of your project stuff as well, right? Because that's all written. All right, have a good weekend.